So quite a few of you asked about how do you write the explicit equation for a sequence. And as in terms of a sequence that's arithmetic, it's pretty straightforward. It's a linear relationship, and it's pretty much writing the equation of a line that goes through some points. But if it's a geometric sequence, it may be a little bit more intimidating. So I have a sequence here that is geometric, and an important thing to be able to do is to verify whether or not a sequence is indeed geometric or not. And in order to do that, it's kind of helpful to use a calculator quickly and just kind of check. So I have grabbed a calculator here, and I'm just going to take so geometric sequences have a common ratio. And in order to find the common ratio, you basically take a term. So I'm going to take 1250, and you divide it by the previous term. So I'm going to divide that by 6250. And when I do, I get 0.2, which is 2/10, which is 1/5, right? So now it's important that that ratio really be a common ratio. So I'm going to just check it one more time here and make sure it's the same ratio. So I'll do 6250. So you take a term and divide it by the previous term, 31,250. And you can see I get exactly the same ratio again. So I know the common ratio for this sequence is 1/5. That's what I'm multiplying by as I move forward. So the common ratio is 1/5. The other thing I need to know is I need to know what the 0th term is. And this would be true if it was arithmetic. In an arithmetic sequence, I would want the common difference, but I would also need the 0th term. And if I'm going forward by multiplying by 0.2, I can go backwards by dividing by 0.2. So if I take the 31,250, and instead of multiplying by 1/5, I divide by 1/5. I can either divide by 1/5 or I could multiply by 5. I'm going to go ahead and say just divide by 0.2. And when I do that, you can see the number I get, 1,56250. But I want you to also see that if I took the 31,250 and I multiplied by 5, you can see it's the exact same number. So I know my 0th term now is, whoops, went off screen here, 156,250. Let me put that, whoops, let me put this off the screen here so it's not in my way. So I get my 0 term is 156,250. And this is my common ratio. And again, we find that common ratio by taking any term and dividing by the previous term. So at this point, I can go ahead and write down the explicit rule for this geometric sequence. It is any term is going to equal exactly the 0th term, which is 156,250, times the common ratio of 1/5 raised to the power n. And just take a minute just to appreciate how well this does exactly what it needs to do, right? So this is the term before any terms in the sequence. It's the 0 term. But if n is the number 1, right, then I would find the first term. If I put a number 1 in there, that's 156,250 times 1/5, which gives me exactly this number. And then if I do increase by 1 to get the second term, right, if I increase n by 1 and I put a 2 in there instead, it's going to take this number 156,250 and multiply by 1/5 1/5. It's going to multiply by a fifth twice. And when n is 3, this formula is going to multiply by 1/5 3 times. And I think the important thing to remind ourselves of is that exponentiation shows repeated multiplication. So if I have a 3 there, right, what is that equivalent to? It's equivalent to 1/5 times 1/5 times 1/5. So when x is 3, it literally takes the 0 term and multiplies by a fifth 1, 2, 3 times. And you can see all these numbers hit the sequence. I think I can do a thing where I say times 0.2 and I press equal. There's the first term, second term, third term, fourth term, fifth term, sixth term, seventh term. So what I know is if I put 7 into this equation, that's kind of a good trick. Let's try that. I'm going to try 1, 5, 6, 250 times, I'll do open parentheses, 1 divided by 5. So there's my fifth. And I'm going to raise it to a specific power. I'm going to raise that to the 7th power. And when I raise it to the 7th power, there it is. I got the number 2. So that was me just plugging it in once. When I evaluate this function once, it gave me the exact value of 2. I can do this as a recursive sequence by doing the thing where I can take the first term or the 0th term. I'll go 1, 5, 6, 250 times 0.2. So when I do this, there's the first, second, third, fourth, fifth, sixth, seventh term. So when n is 7, it's there. So that recursive thing is showing, hey, in order to get to the next term, you do something, right? So let's write that down while we're here. So this is the explicit equation, and it's always going to follow this same pattern for any geometric sequence, right? We're always going to have our 0 term. That's the term before any of the terms are listed. And then this thing right here that's going to be raised to the power is my common ratio. And that common ratio is just any term divided by the previous term. It's worth to make sure, though, it's worth it to make sure that you really do have a geometric sequence. So check a couple spots in your sequence, and you can see I checked 2 in mine. So how do I write this down recursively? Well, to write this sequence down recursively, I need 2 things, right? I need to tell people where it's starting. So this sequence starts at 31, 250. So you have to give it the first term, and then you can write down the recursive step, which looks like this. In order to get to the next term in the sequence, not the nth term, but the one after that, to get to the next term, you simply take the term that you are at, right, and you multiply it by not 1/2, by 1/5. So I have both the first term and the recursive rule. So this together, right, is the recursive definition for the sequence. Start at 31, 250 and keep multiplying by 1/5. So those are the 2 together, right? The explicit equation and the recursive equation. That's all I have to say about that.